All right, so I have written here a second order ordinary differential equation. A second order because the highest derivative is the second derivative, so second order, and ordinary meaning that we are using uh, ordinary derivatives rather than partial derivatives. And so uh, with differential equations, what you're trying to do instead of having something of the form like 10 equals 2x and then you solve for x, instead what you have is you have well, we can see here we have these f of x, which are functions, and we want to find which of these what function uh, actually satisfies this differential equation. So it has to be a function such that the second derivative of the function plus some other function of x times the first derivative of our function plus some other function of x times our function of x that we're interested in equals 0. So we have to find a function that actually satisfies this equation. And so in this video, I'm going to talk about how we do that using what is called a power series. So a power series. I'm not going to go through a lot of the other methods for solving differential equations that you would get if you took a differential equation class, because this playlist is more interested in getting to a point of differential equations that we can actually start using it in quantum mechanics. And so my focus overall is going to be looking at things like the Hermite polynomials and the Legendre equation and Bessel functions and things like that. So I'm not going to go through in detail things like, separation of variables and all that kind of stuff that you would go through in a differential equations class. So I'm jumping sort of right to power series here. And a power series is something where, so I'm going to say that our function f of x that we are interested in, I'm just going to put that as y. And so a power series is something of the form where we have y equals a naught plus a1x plus a2x squared plus a3x cube, and then continuing on till we get to the point. Uh, so, so the general form of an xn, but then this will continue on to infinity. So as n goes to infinity. And so we want to, I want to differentiate, well, maybe that's not the right word. I want to sort of show that there is a difference between a power series and a polynomial. This is a little bit of a side tangent to what I'm actually going to do, but a polynomial is sort of essentially a power series, so a naught plus a a1x plus a2x squared, and so on, going up to an xn, but then it terminates there. And so a polynomial, so we could say a power series has the form that it's a summation from n equals 0 all the way to infinity of a n x n, where a polynomial is instead a summation from n equals 0 to some other arbitrary n of a n x n, like this. And so this is a polynomial, and this is a power series. So we're going to be focusing, though, on the power series here. So like I said, this was just sort of a side tangent, but I find that there's a lot of times when you're looking into the difference between a power series and a polynomial that a lot of math books and so forth use a lot of fancy language, but essentially a polynomial is just a power series that terminates at some point. It doesn't go to infinity. Or you could even say maybe that anything a n plus 1 and beyond is going to equal 0. And you could have zeros within this too, so you could have a2 be 0. So if you had a polynomial that was essentially something like a1x plus a3x cubed, then you're missing that a2x squared. But anyway, this is getting a little bit off topic. I want to focus here on the power series. And so the first thing I want to do to sort of show how to use the power series, I'm actually going to take a first order ordinary differential equation. So we're not going to have this second order here. And so a first order would just be, we would have this function here and dy, so I'm using f of x equals y. Just remember that y is just some function of x, dx, plus q of x, and then y equals 0. And so this is our first order ordinary differential equation. And so what I'm going to do is I'm going to set p of x equal to 1. So these right here, the p of x and the q of x can be they can be functions of x. I mean, this is technically a function of x. It's just saying that at every x we're just getting 1, and so we're setting it as a constant, and then q of x I am going to set as -1. And so what that ends up being is we have dy dx plus y, or actually it should be minus y rather, so minus y equals 0. And then if you just add y to both sides, what you end up getting is you have dy dx equals y. And some of you may already know what we will end up getting as our function of x, what y will equal. So like I said, in differential equations, we want to find out what does y equal, what is this function. So what is our function of x, our function of x? We need to solve for the function rather than solving for some variable. And so we can use the power series. So like I said, we first have y equals a naught plus a1x plus a2x squared, and so on, going to infinity. And then we can also take the derivative of y with respect to x, and we can actually do that term by term. And so what we will have is we have dy dx is equal to d dx of a naught plus d dx of a1x plus d dx of a2x squared, and so on, going to infinity. And so And so with this, if we just go through term by term differentiating, what we end up with is dy dx is equal to, so the derivative of some constant is going to be 0, so that just cancels out. D dx of a1, so that x is going to cancel out, so the derivative of x with respect to x is 1, and so we just end up with a1, and then d dx of a2x squared is going to be 2a2x. Then if we did 3, what we would end up with is 3a3x squared, and so on, going to infinity. And so, well, what we end up with is sort of the general. I guess if we want to continue this, we would end up with essentially n plus 1 a n plus 1 xn, and then that will go on to infinity. So this is sort of the general form of it. And since we said that that dy dx is equal to y, we can actually we can actually set these equal to each other, and we can set each term equal to each other such that that a1, which is our first term here with no x, so we're going to set each power of x equal to each other. So a1 with no x and a naught with no x. So we say that a1 is equal to a naught. And then we also have that a2, so our a2, which is the x here, and then the a1, which is x here, plus that constant 2. So we have a2 equals a1 over 2. So I'm just dividing both sides by 2 here. And then we also have that, so we already know that a1 is equal to a naught, so we can actually set this equal to a naught over 2. And then if we have a3, that equals a2 over 3. Because we have this this 3a3x squared and then this a2x squared. So if we divide both sides by 3, then we end up with this a3 here equaling this a2 divided by the 3. But we already know that a2 is equal to a naught divided by 2. So we can actually set this to a naught over 2 times 3. And so you will see that we will end up with sort of a general form that is a(n) equals a naught over n factorial. And so we can say that this has sort of an implied 1 here. So these all have this sort of implied 1 here, but that doesn't change the factorial. Because anything times 1 is just itself. But anyway, we end up with this sort of general form right here. And so what we end up with is we have y equals, and then we can have, we can sort of factor out our a naught here, and then that is just multiplied by 1 plus x squared over 2 factorial. So we're just putting this coefficient in with the x at every term, plus x cubed over 3 factorial, and so on, going to infinity. Or I guess to make it a little bit more explicit, we could have x over n factorial plus going to infinity, where this a naught is factored out. This a naught here is factored out, but that would just get multiplied or distributed to everything along here. And this is something that you may recognize. So if you've ever taken like a calculus class before, this right here is the power series of e to the x. And so our function y is a naught e to the x. That will satisfy our first order ordinary differential equation. And that makes sense because, like I said, if you take in a calculus class, you know that dx of e to the x is just equal to e to the x. And we said that our differential equation is d of our function, which we have said is e to the x with respect to x, is equal to our function. And that's what we have right here. d dx of e to the x is equal to e to the power of x. And so that satisfies our differential equation. So now I want to go through one that's a little bit different. And so if we take our sort of general differential equation here, the second derivative of our function with respect to x plus p of x times the first derivative of our function of x with respect to x plus q of x times our function of x equals 0. And so if we take this, and now I want to sort of show how to do a second order ordinary differential equation using power series. And so in this case, we will keep our second derivative here, and I will set p of x equal to 0 and q of x equal to 1. And so some people might already know where this is going, but what we end up with is we end up with the second derivative, and I will just use y for our function just to make things simpler, plus y equals 0. And so this is the differential equation that we want to solve. We want to find some y that will satisfy this differential equation. And so once again, we want to use the power series, which as usual is y equals a naught plus a1x plus a2x squared plus a3x cubed, and so on up to an xn, and then off to infinity. All right, so now what we want to do, so first we want to take the first derivative of this because we need to do a second derivative. We'll sort of go piecemeal here. So the first derivative of this is the same as what we found in the last example, and so we will end up with a1 plus 2a2x plus 3a3x squared, and that will keep going off to n plus 1 a n plus 1 xn. But then we want to take the derivative of this right here, and so we will take the derivative, if we take the second derivative of y with respect to x, well, now this a1 is going to go away because that's just a constant, and then this we will have our 2a2x, the x will just go away because once again we're just differentiating term by term. So we end up with 2a2 because that the dx of x is just going to be 1, so that becomes a constant. Plus, and now we are taking this 2 down to the front of that, so we have 2 times 3a3x, and then plus, then we will have plus 3 times 4a4x squared. And then this will keep going until we get to the sort of general form, which is n plus 1, n plus 2, a n plus 2 times x to the n. And then obviously that will keep going off to infinity. So in both cases, this should be going off to infinity. And so this is the second derivative. And we said that, well, we want to find where the second derivative plus of the function plus the function is equal to 0. And what will satisfy that is if we have if we just add each of the same powers of x, so 2a2 plus a naught plus 2 times 3a3 plus a1 plus, and that should have an x here, plus the 3 times 4a4 plus a2 x squared, and then that will keep going till we get to n plus 1 n plus times n plus 2 times n plus 2 times the a n plus 2, and I will put a square bracket around this, plus a n, and then that will keep going off to infinity. So this is sort of the general form where we've taken the actually this should still have an x, and that will be an x to the n going off to infinity. And so this is the from the first term here is from the second derivative, and then this one is from the actual function. And this is just grouping powers of x with each other. And so we want to make each of these coefficients be equal to 0. So we want this to be equal to 0. We want this to be equal to 0 because, and I'll make it more explicit here, that this all has to be equal to 0. Because this is our differential equation here. This is this right here. We're just adding them up term by term. And so that has to be equal to 0. And it has to be true at any x, and so x can't be 0 on any of these, so these coefficients must be equal to 0. And so if we have that, then we have 2a2 plus a naught is equal to 0. And then if we sort of subtract 2a2 from each side, we have a naught is equal to minus 2a2. And so then we can set a2 in terms of a naught, so a2, we can set that in terms of minus a naught over 2. And so that's how we can find out what our a sub 2 is there. And then we can do the same thing for, so if we have our 2 times 3a3 plus a sub 1 equals 0, then we can use that to say that a sub 3 is equal to minus a sub 1 over 2 times 3. And then if we have our a sub 4 here, so that will be a sub 4, which we have right there with 3 times 4 out front, plus a sub 2. Then we can get our a sub 2, or our a sub 4 is equal to minus a sub 2 over 3 times 4. But we already know that a sub 2 is equal to a sub naught, or minus a sub naught over 2. And since both of these are negative, we can actually set this to a sub naught over 2 times 3 times 4, and that becomes positive because these are both negative. So negative a sub 2 would just be negative a sub naught over 2, which makes it positive. And so we end up with well, I guess we can do one more example just to make things clearer. So if we have a sub 5, that will end up being a sub 3 over 4 times 5. And then that will end up being a sub 1 over, so that should actually be, so that'll be 2 times 3 times 4 times 5. And so you can start seeing that that all these odd coefficients are in terms of a sub 1, and all the even ones are in terms of a sub naught. And so what we end up getting if we group everything based on whether it's even or odd is that we have our function y is equal to a sub naught multiplied by 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and you get this alternating plus and minus on the even here, and then that will all be plus a sub 1 times x minus x cube over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus, once again, alternating pluses and minuses. And now, once again, if you've taken calculus, you may recognize these power series as this one is cosine of x, and this one is sine of x. And so our function y is going to be a naught cosine of x plus a 1 sine of x. So this function here will satisfy our differential equation, which, if you remember, was the second derivative of y with respect to x plus our function equals 0. And this should make sense because if our function is a naught cosine of x plus a 1 sine of x, then the second derivative would have to be minus a naught cosine of x plus a1 sine of x. So plus, and if you take the derivative of cosine, or the second derivative of cosine with respect to x, you end up with minus cosine of x. And if you take the second derivative of sine with respect to x, you get minus sine of x. Uh, and so a lot of this is something you will run into quite often in differential equations, is that we use these sort of alternating derivatives. So e to the x is something that pops up constantly in differential equations because as we showed before, the derivative of e to the x is just e to the x. And so by using e to the x, when we end up with a lot of these things where we have derivatives and second derivatives uh, added to the function, we want our function and our derivative to be the same. And so the same thing with the sine and cosine, where we have the alternating, so the derivative of sine of x is just equal to the cosine of x, and then the derivative of the cosine of x is just equal to minus sine of x, which then, if you used even higher orders of differential equations, it would actually go back to being sine of x. So if you take the derivative of this, then you get minus cosine of x. Take the derivative of that, it goes back to sine of x. So you have that alternating sine to cosine to minus cosine to sine, and so it just repeats over and over. And so these sort of repeating function to derivative things like this is something that you find it a lot in differential equations because it satisfies so many differential equations. And so this, so in this video here, I want to sort of just I I wanted to sort of show how to use power series to actually find the functions that satisfy differential equations. So in the first one, we just did the first order differential equation. We found that if we have dy dx equals y, that e to the x satisfied this, and we could find that using the power series. And we found that the second derivative of our function with respect to x plus our function equals 0, which would be the second derivative with respect to x equals minus y. We found that the sort of general solution of a naught, and we could put a naught here as well, a naught cosine of x plus a1 sine of x was the function that satisfied this. So y equals that. And so the main thing I wanted to show is that we can use power series to solve these differential equations, because once we get into some of the sort of, I guess, special functions, as they are sometimes called, that power series is sort of a very standard way of sort of analyzing these differential equations. And that will be important when we start using this stuff in quantum mechanics, which is sort of the motivation behind these differential equations videos here. And so I hope you found this somewhat enlightening, and I will see you in the next video, where I am going to talk about the Legendre differential equation. So I will see you then.